There's one structure which has endured since ancient times, an essential element of buildings and bridges alike, the arch. The arch's strength lies in its shape, and over the years it has proved one of the most reliable forms of construction known to man. In this programme, we travel to Cologne Cathedral to explore the Gothic arch, and to Hamburg to see how, using modern materials, arches have evolved. But we start with the civilization who were the first to really exploit the concept of the arch on a large scale, the Romans. This is the magnificent Pont du Gard near Nîmes in the south of France. Upon seeing the bridge, the 18th century philosopher Jean-Jacques Rousseau said he felt lost like an insect in the immensity of the work. It formed part of an aqueduct 50 kilometers long, which supplied water to the Roman town of Nemesis, now known as Nîmes. It's the highest bridge the Romans ever built. It's an incredibly striking structure, 48 metres high, with 3 tiers of arches to carry the aqueduct at the top across the river. These are classic semicircular Roman arches. In all, there are 6 across the bottom level, 11 in the middle, and 35 across the top. The longest span is 24.5 metres, among the longest spans of any bridges built by the Romans. The aqueduct was thought to have been built during the 1st century AD and was needed to cross the river Gard, a tributary of the Rhône. With arches, the Romans discovered a simple and effective method of bridging space. But the valley was much too wide to be crossed by a single span, so the Romans solved this problem in the highly practical way that characterizes many of their major building works. The aqueduct simply consists of lots of arches which together bridge the valley. You can see that a footbridge has been built next to the aqueduct, almost doubling its width. This was done in 1747, and its stone arches exactly echo the originals. In fact, it's quite a sympathetic add-on, and it doesn't detract from what we're here to look at. The arch itself is made up of these stones here. They're all slightly wedge-shaped, and together they form a semicircle from this pier to that one over there. Stone cracks easily when it's pulled apart, but when it's compressed, it's immensely strong. The arch works because each stone pushes against its neighbour, and the weight is carried outwards and down. When the forces reach the end of the arch, they're taken down the pier to the ground. The thickness of the stones making up the arch are crucial to whether it stands or not. These are over 1 metre thick, approximately 1/20th of the span of the arch. The Romans never made sophisticated calculations, but they knew from experience that if the stones were any thinner for an arch of this size, the arch would be at risk of collapsing. Once built, an arch is incredibly strong. It can support a lot of additional load on top, but the weight has to be spread across it, and that's what these solid parts are for, called spandrels. The spandrels are not part of the arch, but they just transfer the loads from above into it. So it doesn't matter what they're made of, and behind this stone facing is just compacted rubble filler. The Romans were expert builders, and the Pont du Gard must be one of their greatest achievements, especially when you consider that the technology available to them was limited. The arches were built on wooden scaffolding, which carried the weight of the stones until the last stone was dropped in at the top, the keystone. Once the scaffolding was knocked away, the arch would stand, hopefully. Although these arches are among the largest the Romans ever built, their span was restricted by their equipment. The stones were lifted up into position using wooden cranes worked by teams of slaves. The biggest crane the Romans had could only reach around 15 meters. So if you had one crane on each side, the biggest arch you could build was less than 30 meters. At the top, the water channel is just 1.25 meters wide and over 1 meter deep. It's the only part of the aqueduct that uses mortar, needed for waterproofing. Originally, it would have had a stone roof, but much of this is now missing. Looking along the aqueduct, you can see that it's developed a curve towards the upstream side. This is because, over the centuries, undermining of the piers has caused the bridge to lean over ever so slightly. But masonry is extremely robust, and it would take much greater movements than these to cause it to actually collapse. The Romans' major contribution was in the construction process, the organisation and techniques which were used, rather than the development of new design concepts. The Roman engineers learnt from experience, setting out their arches using geometrical rules. This system was highly effective, perfectly suited to their needs, and the Pont du Gard is the finest expression of this. The Pont du Gard is a celebrated object of beauty, a remarkable piece in the huge jigsaw of Roman engineering. They were the first civilization to understand the value of the arch, and their use of it as a fundamental building block in much of their construction is an enduring part of their legacy. This aqueduct and the other structures they created across Europe are a lasting monument to their skills. The fact that bridges such as the Pont du Gard still stand is also a testament to the strength of the arch. Once built, they will pretty much stand forever, or until the stone finally weathers away. But over the centuries, changes in building styles have forced the arch to evolve. Nearly 1,000 years later, in a new phase of monumental construction, the arch found a major new expression. The 12th and 13th centuries in Europe saw an extraordinary explosion of architecture and engineering, driven by merchant wealth and religious fervour. This was the High Gothic Age. Many of our greatest cathedrals date from this period, including this one, the imposing Cologne Cathedral in Germany. It has a highly decorative, even extravagant exterior, but all this decoration is actually concealing quite a simple structure of arches and vaults, which owes much to the Romans. Like the Pont du Gard, the structure of Cologne Cathedral is entirely based on arches, but the crucial difference here is that the round arch has been replaced with a pointed arch. This was a vital development which allowed a different form of building altogether, a building which was light and spacious, but above all, which was high. All this was achieved because the pointed Gothic arch carries the weight more directly to the ground. It's a much more efficient shape, so it can be much thinner. In addition, the symmetry of the arched vaults and the clean vertical lines of the piers give Cologne Cathedral its particular elegance. Cologne Cathedral has its roots in the great French cathedrals of Notre Dame and Amiens. The choir here at the East End was started in 1248, but it took another 600 years for the towers at the West End to be finished. In reality, work on this building never stops. There's a local saying, which loosely translates as, "When the cathedral is finished, the world will end." In the great cathedral building boom, new skills and techniques evolved. Stained glass windows and high arched stone ceilings grew ever wider and more magnificent as towns and cities tried to outdo their neighbours. That these structures have lasted nearly 1,000 years can be attributed to the knowledge and experience of the stonemasons who built them. Stone was shipped down the Rhine from the Drachenfels, 40 kilometres upriver. The master mason supervised the whole construction, combining the modern role of engineer and architect and organising the teams of professional craftsmen on site. They were highly sought-after men. Cologne Cathedral was laid out by Master Gerhardt, who had visited France, where he studied the techniques used in building the French cathedrals. By the time of his death in 1260, the cathedral was beginning to take shape. Although many master masons followed Gerhardt, it was his vision which we see in the layout of the cathedral. The rules of proportion used in the design were originally developed by the Greeks and were handed down from generation to generation in the Masonic lodges. It wasn't until much later that people began to understand, in structural terms, why they worked. What the masons knew was that a building built strictly according to their geometric rules would stand up. But building this high created new challenges. The weight of the roof on the tall vertical piers pushes them outwards, so the piers have to be supported in some way from the outside. Because the cathedral is so much narrower at the top than at ground level, where you can see all the extra space in the aisles, the supports for the roof have to span right over the lower level. So a new development was needed, a Gothic invention, the flying buttress. All around the perimeter of the cathedral, the upper levels are supported using these flying buttresses. In fact, these are flat arches, and they work very effectively. The force outwards is concentrated where the roof and the vault meet the pier, here. The force is carried down the arch, like this, and the weight of the buttress directs the force down to the ground and stops it toppling outwards. The pinnacle is also a nice detail. It adds weight to the top of the buttress to stop the arch breaking it off. The cathedral has survived through some difficult times. There was damage during the Second World War when 10 vaults in the nave and north transept collapsed. One bomb damaged the tower so badly that it had to be bricked up, and it has been left deliberately in this condition as a reminder of those years. There's currently a major program of restoration underway. Many of the pinnacles have been repaired, including that one, the top of which fell off in an earthquake in 1992. There's also a plan to protect and clean the whole building, but without changing its overall appearance. Over time, pollution has turned the cathedral almost black, and this has given it an almost foreboding appearance. Nevertheless, Cologne Cathedral still remains remarkable in its details and awe-inspiring in its scale. With just simple hand tools, wheelbarrows and winches, the builders of these Gothic cathedrals realized the most complex industrial projects in Europe since Roman times. Their organization of the site itself into teams of paid professionals rather than slaves was fundamental to their success. But for me, it's what they achieved technically in a pre-scientific age that's so extraordinary. Because of their strength, steel and concrete have now largely replaced stone as a building medium. But where great spans are needed, the arch is still an extremely attractive solution. This is the jumbo shed built for Lufthansa Technik, the engineering wing of the German airline. It takes 3 planes, including 2 747s, and is one of the biggest aircraft hangars in the world. Forming the heart of a base here which employs over 5,000 people, it was opened in August 1992 at a cost of 172 million marks, over £60 million. The design of this enormous hangar posed some real engineering challenges. Lufthansa wanted to be able to open the whole of the front of the building to get the planes in and out easily. Secondly, the height of the building is restricted by airport regulation. This meant the roof had to be supported in a rather special way. Instead of columns underneath, two huge steel arches hold up the front of the roof. The roof frame is suspended from the arches by hangers, rather like the deck of a suspension bridge. The arches are positioned towards the front of the building because the doors can't carry any weight, but the back of the building is held up on ordinary columns. The arches span 180 meters from one side of the building to the other. They sit on 4 A-shaped supports, 2 at either end of the building, and the arches get additional stability by leaning together and being joined with struts. Just crossing the threshold through these huge doors and into this giant hangar, it's quite spectacular. A jumbo jet is 7 stories high, but it's dwarfed by the height of this roof. This one's covered in platforms and machinery, spaces for men to work. This is where the third plane goes, right here. The hangar is used to service primarily jumbo jets. Working 18 hours a day, it takes 7 weeks to totally refit a plane, and it costs £3 to £4 million, not counting the engines or the paintwork. The construction of the building was quite ingenious. The whole roof, with the arches, was built out here on the ground, while the foundations were laid on site, saving time and money. The roof was then slid on rails into its position and lifted up using hydraulic jacks onto the A-frames on either side. The arches are simply massive. Together with the roof, the whole weight is 2,800 tons. That's the weight of 18 empty jumbos. You can see the struts joining them together. This gives them a lot of rigidity, stiffening the whole roof from sway from wind loads pushing the building sideways. The hangars are inclined from the arch down to the joints here where they meet the roof frame. This is to keep them in line with the frame, which runs straight along the building. The hangars distribute the weight of the roof along the arch, just like the spandrels on the stone arches we saw at Nîmes. This arch is much longer and flatter than the rounded arches at the Pont du Gard or the pointed Gothic arches in Cologne. And you can see there are no buttresses on the outside of the building. So how does this arch stand up? It's an ingenious solution. The arch is like a bow on its side, and the roof frame acts as the bowstring, tying the ends of the arch together. Here at the end, the force down the arch meets the support, and the arch tries to push outwards. This steel link ties the arch to the roof frame, which you can just see sticking out of the building. The push outwards creates a pull in the roof frame right through the building. This is the bowstring effect, which allows the arch to sit on these flat bearings here without a buttress. We're right underneath the roof here and right on top of the jumbos. You don't often get to see them from this angle. It's the workhorse of the world, the 747, and it gets refitted every 6 to 10 years. This one's nearly finished. Another 5 days and it'll be off to the paint shop. The roof frame itself is made up of trusses which run along the building and across. This is one of the two which are connected to the hangars up above. Being this big gives the roof the stiffness it needs to support the cranes which carry engines and other heavy equipment around down there. This is one of the access platforms underneath the roof. Can we go down, please? Get a great feel for the size of the hangar here. The hangar in Hamburg is a prestigious building, a centerpiece for Lufthansa's technical operations. It's a structure in the public eye, a showcase of engineering confidence, clearly visible to the passengers in planes taxiing by. The great space could have been bridged using more standard beams and trusses, but the result would have looked like an industrial shed. The arch, as always, has a natural beauty. The arch is a pure and simple form. As we've seen at the Pont du Gard in Cologne and here, it derives its strength from its shape. That shape has evolved over the centuries as new materials and our understanding of its behavior have developed. As well as a glorious past, the arch has a great future. In our next programme, we explore a 19th century masterpiece by Isambard Kingdom Brunel, the Clifton Suspension Bridge. We admire the magnificence of the vast new Storebelt Bridge in Denmark and enjoy the slender elegance of the Swiss Bay Bridge in the Czech Republic. Here, in the shadow of Mount Vesuvius, near Naples, is where the Romans invented modern concrete, a material which was to shape the course of their monumental architecture. In this programme, we visit France to explore the stunning Plougastel concrete arch bridge at Brest. We marvel at the breathtaking design of the airport railway station at Lyon. But to discover the Roman origins of modern concrete, we need to start in Italy. Early concrete had been used by the ancient Egyptians and the Greeks, but it was a chance discovery here by local builders using these volcanic soils that led to a critical new development in the history of construction. Concrete is made by binding sand and stones together with an adhesive which is called cement. Early Roman builders had made basic cements using lime, sand and water with some success, but across the bay, near the Roman port of Pozzuoli, builders found that their concrete had a much greater strength than anyone else's. The secret? They discovered that by using sand from the volcano rather than ordinary beach or river sand, they could create a much stronger material. It would even set underwater. By the middle of the 1st century BC, the new cement, named pozzolana after the town, had become a key element of all major Roman construction. The Romans didn't understand the chemistry, but the volcanic sand changed the chemical reaction in the setting of the cement. It's this that gave their concrete its special properties. Their new discovery was a concrete of unprecedented strength, and it heralded a new era, paving the way for some of the greatest buildings of the Roman Empire. This is the amphitheatre at Pozzuoli, the town where the new concrete was first discovered. Begun under Nero and completed just before the famous eruption of Mount Vesuvius in AD 79, the building has stood for nearly 2,000 years. We're here because it has some of the best preserved Roman concrete work anywhere. The amphitheatre is a great oval shape, 149 metres long and 116 metres wide. It could seat 20,000 spectators. It was used primarily for fights between gladiators and wild beasts, which were kept in rooms underneath and lifted up into the arena through hatches in the floor. On first glance, it looks as though the amphitheatre is built entirely from brick and stone. But this is deceptive. In fact, the bricks are largely just a facing. These walls are made of concrete with a tile or a brick facing. The concrete was made in a stiff, wet mix and placed by hand in position. The tiles on the outside and on the inside were to stop the concrete slumping outwards, providing just enough lateral support for the relatively short time it took the concrete to set. That way they could build the whole wall up continuously. Cement actually works because chemical reactions form crystals when water is added to the dry mixture, and these stick to everything they touch. It's a bit like wet sugar, which when it dries gets sticky. It can stick a spoon to a saucer, for example, like this one. Like modern cements, the Roman pozzolana actually absorbs water during this crystallization process, which is why it can set underwater. Concrete gets its strength from the cement, but also from the mixture of stones inside it. Down here, you can see concrete with some quite large stones in it. The different sizes of sands, gravels and stones means that the whole mixture becomes interlocked and dense when it's compacted. The smaller stones simply fit between the larger ones, and the cement glues it all together. As well as walls and foundations, the Romans realized that their new concrete could bridge spaces. Domes and vaults became less expensive and simpler to construct, leading to a new and grand architecture. To build a vault like this, wooden shuttering would be constructed underneath and the wet concrete poured or placed on top. The shuttering had to be very strong because it had to carry the whole weight of the roof until the concrete had set. Sometimes, if the wooden planks weren't perfectly smooth, they would leave lines in the roof showing where the wooden supports were positioned. In their buildings, the Romans used brick, stone and concrete together for both decorative and structural reasons. But because concrete can be molded to any shape, it is often used largely as a structural filler, hidden behind brick and stonework. Because of this, the extent of the Roman use of concrete in their monumental buildings is still not well known. Perhaps the greatest advantage of concrete over the earlier building materials like brick or stone is that all you had to do was to bring the loose materials to site and mix them with water. Like all construction, even today, the cost of bringing materials from a long distance like stone from a quarry, can be huge. If you can use local sands and local gravels and mix them together in a bucket and make a new material that's nearly as strong as stone, but in any shape you want, that's concrete. The Roman process of making concrete wasn't bettered until the 19th century, when a deeper understanding of the chemistry of concrete allowed modern cements to be developed. But the principles of modern concrete are exactly the same, and the next major evolution was to discover how to reinforce concrete to make it even stronger, as we shall see next. During the second half of the 19th century, a new concept emerged, which was to transform the character of architecture and civil engineering, indeed of all modern construction. It was to reinforce plain concrete with iron or steel, creating a new material with properties which combine the best of both. Here in Brest, in northern France, is the Pont de Plougastel. Completed in 1930 by Eugène Freycinet, it broke all records for a concrete bridge. It's an extraordinary monument to Freycinet, a brilliant civil engineer and one of the pioneers of reinforced concrete. It comprises 3 huge concrete arches, each spanning 190 metres, with a double deck across the top designed for road and rail traffic. The arches are high too, with a rise of 35 metres in the middle to allow ships to pass underneath. In the 1980s, it was decided that it was too narrow to be upgraded as a motorway bridge, and a new cable-stayed bridge runs over the river nearby, leaving the old bridge for pedestrian and cycle traffic. As we've seen, the use of concrete as a building material can be traced to early civilizations. But it was only during the 19th century that it was realized that by embedding iron bars deep enough in a concrete, they would be protected from rusting, and it would create a material with strength and durability for really large structures. This is a piece of old reinforced concrete, and you can see the steel bars sticking out the end. In fact, they run right along the length of the beam, buried inside the stone. These have rusted because they're exposed to the air, but inside they'll be as good as new. Although concrete is extremely strong when it's compressed, it cracks easily when it's stretched. The idea of the steel reinforcement is that it carries the pulling or tensile forces in the concrete. It's a very efficient system because the combination of steel and concrete working together is much stronger and stiffer than either of them working independently. The Plougastel Bridge was a turning point in the use of reinforced concrete. Prior to this, it was simply not believed that it would be possible to build a concrete bridge so big. Freycinet argued that a concrete bridge would be less expensive and lighter than a steel bridge. He was also convinced it would be strong enough. By the 1920s, Freycinet had learnt how to compact his mixture of stone, sand, cement and water to make a concrete with a strength of up to 50 newtons per square millimetre. That's as much as some rock, and more than twice as much as had been possible at the turn of the century. Reinforced concrete is made by pouring concrete into a mould in which the steel reinforcement has already been positioned. To do this out over the river was a real challenge. He designed a huge wooden arch resting on concrete pontoons, like this, which could be floated out into the river and was used as a mould for the concrete arches, which he built one at a time. The sides of the arch were built out from the bottom, like this, until they almost met in the middle. Freycinet's trick was to leave a gap at the top and to wait for each side of the arch to set. Then, using hydraulic jacks, he lifted the arch off the mould and into its final position simply by pushing apart at the top. After he filled the gap, he constructed the vertical supports and finally finished the deck. And now I'm underneath the deck. This is where the track for the railway would have run if it had been completed. We're right inside one of the big arches, stretching down here, right to the bottom. You can see the arch stretching out down there, getting steeper as it goes. It's a hollow box structure. Because it's made of reinforced concrete, it doesn't have to be solid like a masonry arch. These triangular pieces are where the vertical supports for the deck above meet the arch. Down near the bottom of the arch, it really gets quite steep. That's the bottom just there, and that's the sea. The Plougastel Bridge was also the key to another of Freycinet's innovations, for which he's best remembered. After this bridge, he subsequently developed a system of pre-stressing concrete, which gave it even more strength. This enabled the construction of pre-cast units, which could simply be lifted up and assembled in place. And that's the method they used for the new bridge. After nearly 70 years, the bridge is beginning to decay. But we can't expect it to be pristine, and sometimes, like here, the water can get in along tiny cracks and rust the steel bars, which then expand and spoil off the concrete. It's a bit unsightly, but it's not serious. Despite its appearance, this is an historic bridge. It's a strong and confident design, a marvellous expression of a bold engineering spirit. In building the Plougastel Bridge, Eugène Freycinet had made a huge leap in fulfilling the future potential of concrete. Over the following years, the use of reinforced concrete quickly became widespread. Free to mould the material to their designs, architects and engineers around the world could finally create new shapes which were also inherently strong. More recently, we've come to think of concrete as a mundane, even dull material. Tower blocks and car parks from the 1960s and 70s have put a lot of people off. But it can be quite magnificent. And for me, there's nowhere more exciting to see just what you can do with concrete than here. This is the Satellas TGV railway station at Lyon Airport in France. Commissioned by regional government and the French railways, the building was designed by the great architect-engineer Santiago Calatrava. It's a prestige building which cost nearly £15 million, but the result is a station that is simply unique. Completed in 1994, the station was the subject of an international competition. Its importance is apparent from its design and its location. It stands squarely across the main access road to the airport, which has to run straight through it. The complex forms a strategic transport interchange for the whole region, incorporating the airport, a nearby motorway, and the main railway line on which the station stands. To the side are the tracks for the stopping trains, and in the middle are the high-speed TGV lines, these ones here. These through trains run at 300 kilometers an hour, so they're segregated from the others, running in a tunnel to protect the people in the station from the noise and shock waves. Approaching the building, it is immediately apparent why it has achieved such prominence. There is an extraordinary quality to it, a feeling of dynamism and movement, almost uplifting. The whiteness of the concrete mix makes it look even more like a sort of skeleton, fused onto the foundations below. Spanish-born Santiago Calatrava studied sculpture while reading architecture and later turned to civil engineering. In a relatively short career, he's become well known for his outstanding design of buildings and bridges, structures which combine the functional and the aesthetic, and which, like this one, have sculptural qualities. Under the great winged section in the centre is the main concourse with its magnificent steel and glass roof. There are some wonderful details. But what I want to show you is Calatrava's use of concrete, and for that I need to find the platforms. Unpainted white concrete ribs stretch over our heads, looking like the vaulted roof of a cathedral, but with openings which create dazzling patterns of light and shade all over the floor. You would never have thought of building a white station in the days of steam trains. As we've seen, reinforced concrete has strength in bending as well as compression, and this is where we can see that used to best advantage. The curved shape of the roof, and particularly the tapering props on either side, reflect precisely the forces they're carrying. They're thicker at the top, where the bending forces are greatest. This aspect is why people have commented on the natural quality of this design. But to see the whole structure, we need to go outside. The choice of concrete is quite deliberate. It feels solid and substantial, but it also gives the building weight and stiffness to cope with the dynamic forces generated by high-speed trains passing behind that wall. But there are many aesthetic details here too, which are unusual in concrete. These great inclined legs on the outside support the edge of the roof, but their shape is carefully echoed on the opposite side, right along the central wall. It is this attention to detail which really characterizes good design. The handrails show us just what a marvelous material concrete can be. Here you can see the true nature of concrete, reconstituted stone. The finish is absolutely superb, as are all the other structural details. Calatrava is a master of elegant structure, blending art, architecture and engineering. With the TGV station at Satolas, he has brought the use of concrete forward into an artistic perspective, creating shapes of great beauty out of a material we most often associate with simplistic and functional buildings. In the hands of a master, concrete can be a marvelous material. To take stone and fuse it together with a cement was an ingenious idea. To add steel reinforcement allowed engineers to create a material which was extremely versatile. Made with care and attention to detail, concrete can also be stunningly beautiful. It hasn't all been plain sailing, but here, finally, concrete has come of age. In our next programme, we travel to Italy to one of the greatest of the Roman public spaces, the amphitheatre in Verona. We discover the delights of the Victorian Palm House at Kew Gardens in London and admire the spectacular World Cup sports stadium at Bari in southern Italy. Our enthusiasm for recreation and sports over thousands of years has led to the creation of some of our grandest and most impressive buildings. In this programme, we visit one of the finest Victorian garden buildings, the Tropical Palm House at Kew in London. Travel to Italy to the futuristic vision of the San Nicola football stadium in Bari. But we begin here at the magnificent Roman amphitheatre in Verona. The arena is the mightiest of Verona's Roman monuments. Dating from the 1st century AD, it survives in remarkable condition, thanks mainly to the deliberate policy of preservation, which began in the 13th century. It's in such good condition that it's still in regular use today, particularly during the opera season in the summer. The arena's original capacity of some 30,000 people gives an idea of the importance of the town and its amphitheatre in Roman times. The arena stood outside the ancient Roman walls, and these are the remains of the main ceremonial entrance facing the town. On the opposite side, you can see the gate leading to the country through which the dead and wounded were taken away. Walking into this fantastic space is an extraordinary experience. The amphitheatre is now at the centre of modern Verona, but all that's invisible from here. It's as if we've been transported back to ancient Rome. The great rows of seats rest on a complex system of vaults and pillars which run right around the inside of the structure. Tall passageways allow people to circulate. Although much of the amphitheatre has been preserved, only a fragment of an original outer wall remains, standing sheer above the neighbouring streets. In Roman times, the arena hosted all sorts of spectacles. There would be gladiatorial fights, boxing matches, baiting of wild animals. This drop separated the people in the lower seats from the action in the arena. The original stone on the exterior and on the terraces is a limestone quarried from local hills and cut on site during construction. It's worn now, but still looks beautiful with pink and white colouring and a soft texture. The huge rows of stone terracing are extremely heavy, and supporting them was a great challenge for the Romans. Under the seats there are vaults made from concrete, Roman concrete, with a stone facing. This is some of the exposed concrete up here. It's strong in compression, so it's ideal for carrying the weight of the seats above, but it cracks easily in tension when it's pulled apart. So to bridge across the passageways, the roof is vaulted with arches which spread the weight to either side. The traditional Roman arch is semicircular. It would have been built up on wooden scaffolding, which was then knocked away from underneath. But there are other ways of bridging spaces. Sometimes they used a stone lintel instead across the doorway, like this huge one here. It must weigh over 4 tons. It works like a beam sitting on pillars on each side of the door. It looks as though it's carrying a huge amount of weight. But here on the other side, you can see the trick. Up there is another round arch which carries the weight of the roof and lightens the load on the stone lintel. So it only has to carry its own weight and the weight of the bit of wall above it. At first glance, this one looks the same, but then you notice there's a wedge-shaped stone in the middle. It's a special sort of arch called a flat arch, and it's almost unbreakable. The 3 stones work like these 3 boxes between my fingers. When you push down on the middle, the arch pushes outwards at the ends, and you can really feel it in your fingers. It works as long as the ends of the arch can't move. Otherwise, it just falls through. These great extensions at the end mean that it's really firmly bedded into the wall and it can't move at all. And the wedge-shaped design is clever because even if the middle drops a little, it still works as an arch and it's perfectly safe. The great walls supporting the high vaults are made of concrete with a stone facing. At the ends of the walls, these pillars are cut stone, partly for style, but they also provide support for the outward forces of the arches. There was an outer wall which ran right around the amphitheatre, but now only this section on the left with 4 arches remains. It looks very precarious, but it's been strengthened with steel bars which run right down from top to bottom, pulling down on the wall and holding it firmly in place. That was done in the 1950s. They're now thinking of replacing the steel bars and rebuilding the arch on the second level, like this. This will give people a much better idea of the original structure of the amphitheatre. Following the Roman period, stone was stripped from the walls for other buildings, and in the 12th century, earthquakes caused major structural damage to the arches. But from the 13th century, efforts have been made to replace the stones. A major restoration is now underway again to preserve the vaults and external stonework. It will ensure that we can safely hand on to future generations this remarkable survivor of an age where much of mass entertainment was a violent and gory spectacle. After the fall of the Roman Empire, the building of such great public arenas died out completely. But centuries later, new forms of recreation emerged, which also required special buildings, although for a rather more genteel purpose, as we shall see next. The Palm House in London's Kew Gardens represents the classic values of Victorian Britain in an age of unprecedented discovery. The British Empire was reaching out to the furthest corners of the globe and bringing treasures of the world home for an increasingly curious public to enjoy. Amongst these wonders were the exotic plants of the tropics. Entirely made from wrought iron and glass, the Palm House is the first building of its kind in the world and is the largest curvilinear glasshouse still standing. Just glancing at the Palm House, two features strike you immediately. It's very light in appearance and it's formed almost entirely from curved surfaces. Its shape was partly for aesthetic reasons, but principally because horticulturalists of the day were convinced that curved glass was best for light. It was designed and built by the special partnership of the architect Decimus Burton and the engineer Richard Turner in 1847. Their task was to create a building which would provide sufficient light and heat for tropical plants, but also allow free access to the general public. The hardest challenge of all was to create the largest possible open, uninterrupted space where the tallest of palm trees could thrive. Turner's expert knowledge of the production of iron was the key to their success. Burton had planned to use cast iron for the frame, but Turner's innovation was to use wrought iron ribs called deck beams, a type of beam normally used by shipbuilders. In fact, the ribs of the Palm House work very much like the hull of a ship, only upside down. It was a great piece of lateral thinking to adopt shipbuilding ideas for the construction of the glasshouse. Thanks to Turner's brilliance, the Palm House was one of the most innovative structures of its day. This main rib reaching up is one of Turner's deck beams. The arched ribs carry the weight of the roof away from the centre and down to the foundations. And from here to the top, it's made of a single piece of iron. The downward force tries to bend the arch outwards in the middle, just like I can do with this cane. So it has to have sufficient strength in bending, what we call tensile strength, to stop it from snapping. The ribs of the main span sit on top of a row of columns on each side of the hall, like these. The columns also support a gallery at the top for viewing the trees. Not only is the gallery useful for maintaining the palms, but it also provided the Victorians with an experience far removed from their everyday lives. Up on the gallery, we can really appreciate how much space there is. You can imagine how people must have felt leaving the grime of Victorian London and finding themselves face to face with a tropical jungle. Burton's original design required additional columns in the central area of the hall. This was because the traditional cast iron ribs didn't have enough strength to span across the whole width needed for the plants. Turner's wrought iron solution allowed for a single span right across the hall without any additional support, removing the need for the additional columns and leaving the space for the trees. Here we can really see the advantages of wrought iron. This capital is bringing the weight of the roof down onto the rib here. If it was cast iron, there'd have to be a column all the way to the ground, right here. The Palm House was one of a series of controversial iron and glass buildings of the day. These structures were not so much built as assembled, using entirely prefabricated components, foreshadowing construction methods often used today.
Another unique feature of the Palm House is the sheer quantity of glass. What had once been a luxury, expensive material was now available in large sheets at low cost, thanks to the 1845 repeal of excise duty on glass. Turner was one of the first engineers to capitalize on this. The Palm House has continued to provide an invaluable resource for scientific study. As a building, it stands as testimony to a pioneering era of new materials and new methods, at a time when Britain was keen to share her preeminence in engineering with the public.
But this was just the beginning of the new age of leisure, an age which would see its clearest expression in the 20th century in the rediscovery of the sports stadium.
This is the San Nicola football stadium in Bari, southern Italy. Built for the 1990 World Cup finals, it holds 58,000 people, all seated. It was designed by the renowned Italian architect Renzo Piano, who wanted the stadium to look otherworldly, like a spaceship that had just landed, or as he described it, a shell suspended in the midst of greenery. It's part of a vast park in West Bari, and there are plans for it to be turned into a sports city. The stadium houses the local football team and also an athletics track.
My immediate impression is of a building which is almost floating, only lightly touching the earth. It's a stunning sight, a perfect combination of architecture and engineering. It's beautiful, and for a 60,000-seater stadium, it feels very compact. What we're seeing here is just the upper stand. There's another whole stand below, hidden by this landscaped hill. In fact, the pitch is 2 meters below ground level. So while the visual impact of the stadium's sheer size is reduced, it serves only to enhance the curves of the canopy and the upper stand.
The great bowl of the upper stadium sits on stilt-like columns underneath. But inside the structure, running inside the perimeter and cleverly hidden from view, is a concrete ring beam holding the whole stadium together. Resembling an open flower, the shell of the upper stand is clearly divided into sections, 26 in all. Each section is separated by a distinctive vertical slot, which provides access to the seating and also provides a glimpse inside the stadium from outside. Each single bay, then, is like the petal of an open flower, giving Bari Stadium its unique appearance.
It's a very exciting structure. At Kew there was a feeling of serenity, even study, but here it's all action. On the pitch you can almost hear the roar of the crowds. The colours in the stand and the light fabric roof all combine to give it a real buzz.
You can see the upper stand clearly suspended over the lower seats. The seating blocks are all precast concrete units fitted onto the shell beneath. Using a combination of prefabricated units and concrete poured in situ, the contractor minimized the cost of construction.
We're underneath the seating of the upper stand, and this is where the ring beam runs around the perimeter inside the great curved shell. It connects these supporting pillars and holds the whole upper structure in place.
The angle of viewing for spectators is very important. They must obviously be able to see over each other's heads. Ideally, the stand would be curved all the way up, but for simplicity, the upper stand is made up of 3 straight sections that get steeper towards the back.
The layout of the stadium is meticulously thought out. No spectator should be more than 190 meters from the football pitch, so that defines the extremities. The most popular place to sit is in the middle on the side, so there are more rows of seats there than at the ends. And finally, the VIPs and the television cameras are always on this side of the stadium, looking east, so that for afternoon games, they have the sun behind them.
Up at the back of the stand, the great steel supports for the fabric canopy arch out over the seating. They're braced against swaying in the wind by the white truss that runs along the top at the end of the arms.
The canopy is a coated glass fibre fabric stretched over the thin arched beams which span from here to the truss at the top. It provides some protection from the weather, and being convex, it adds to the design architecturally by completing the curve of the upper stand below.
Being a membrane rather than a solid roof, it's much lighter in weight. It also lets some light through, reducing the amount of floodlighting needed and adding to its attraction at night when the whole stadium is lit up like a lantern.
Just climbing up over the roof. It's extremely windy because the curved shape of the canopy directs the wind right over the top. And here we are, right at the lip of the roof itself. You can see the floodlights fixed all around the perimeter to illuminate the ground down there. It's a spectacular view. Perhaps this is the best seat in the house. Since the 80s, public safety has become a major concern at football stadia. The first response was to make them all-seater so that crowds on the terraces aren't crushed. Secondly, separation of spectators, both from the pitch and from each other, is a key feature. The Bari Stadium has a moat all the way around the pitch, as well as these dividing walls in the stands. Sad, but necessary.
But the most important safety aspect of a modern stadium is how quickly it can be evacuated. This has to be carefully designed. At Bari, each of the 26 petals has its own exit, and the entire stadium can be evacuated in 5 minutes. The Bari Stadium is a distinctive landmark. The boldness of its design is matched by the skill of its engineering, which has enabled the idea of this floating stadium to become a reality.
The amphitheatre at Verona, the Palm House at Kew, and the stadium here are all buildings that evoke a sense of occasion that perfectly complements what happens within. The buildings are very different, but their purpose is the same: to create an exciting space for entertainment and spectacle. And exciting buildings means exciting engineering.
In our next program, we look at the structure of towers. We start with the medieval towers of San Gimignano in Italy, travel to England to the remarkable Liver building in Liverpool, and scale Europe's tallest office building, the Commerzbank in Frankfurt, Germany.
When space on the ground is limited and money's no object, then building upwards is the only solution.
In this programme, we explore the first true British skyscraper, the Royal Liver Building in Liverpool, and travel to Frankfurt in Germany to visit the tallest office building on the continent, the ultra-modern Commerzbank. But we begin in Tuscany in Italy, where 800 years ago, the quest for height really took off.
The problem in engineering tall buildings is how to make them strong enough to carry their own weight and the huge forces from the wind trying to blow them over. Like this tree, it's a question of stability. As they get taller and taller, they're more and more exposed to the wind, and it gets more and more difficult to support them at the base. In masonry, this is a particular challenge.
These are the spectacular medieval towers of San Gimignano, rising above the rooftops of this beautifully preserved town in the Tuscan hills of northern Italy. 15 of these towers remain out of an original 72, each one the result of merchant wealth and family rivalry back in the 13th and 14th centuries.
Tall buildings are an expression of wealth and status, and by the 13th century, San Gimignano had become one of the most prosperous towns in Europe. On the main route from northwest Europe to Rome, the town was busy with pilgrims and merchants. It was a centre of the textile trade. The piazzas would have been bustling with people in the finest jewellery and fabrics.
The towers were commissioned by the richest families in the town, and they competed with each other to build the tallest. The various towers each had different uses. Some were used as campanili or bell towers, but essentially they were fortified dwellings, safe places of refuge in times of war.
The Palazzo del Podestà was the seat of municipal government and was built at the end of the 13th century. At that time, the town was self-governing, an independent city-state.
The palazzo is dominated by the Torre Grossa, the great tower which is decorated by the arms of the various podesta, or mayors, who held office during its construction.
The building design is actually very simple. Like the other towers in San Gimignano, they're all roughly square and hollow, like this tube I've made from a postcard. The walls are about as wide as they could be without any internal bracing. If the walls were much wider, then towers like these would be at risk of collapsing from the wind. So the square shape is a very strong shape, provided the walls are thick enough.
The walls are actually made of brick, but faced on the outside with a local limestone called travertino. These holes were for wooden scaffolding used during construction.
The tower has 4 massive walls, which are thicker down here near the bottom than at the top. The thickness keeps the stresses in the stone low, but more importantly, it stops the wall from buckling under the weight of the walls above. Having such a large base gives the whole tower stability against toppling. The tower had wooden floors. The joists supporting the floors sat in these larger holes here, but the floors didn't provide any additional support for the tower. In modern buildings, the floors often provide extra bracing, tying the four walls together. But here it's clear the floors had no structural significance because they've gone and the tower is still standing. Up here at the top, the wall has thinned down. The tower is an amazing 54 meters high. That's the equivalent of about 15 stories, near the limit of what's possible in brick or stone. In fact, it's only possible with this design because of their compact shape. They're an amazing sight.
By the mid-14th century, more than 70 towers had sprung up all over the town. It must have been like a medieval Manhattan. It looks peaceful now, but there was intense rivalry and deep divisions between the families. Feuding was commonplace, particularly between the two great families, the Ardenelli and the Salvucci.
These twin towers were built by the Salvucci family. The city rules insisted that no tower be higher than the Great Tower, so, undaunted, the Salvucci family built two, the idea being that their combined height far exceeded anyone else's. However, if they had built one tower that high, it wouldn't have stood up anyway, because it would have been too slender for its height.
They stood next to their palace, which was burnt down in 1352, as the war between the two clans entered its bloodiest phase.
Fighting between rival families was just one part of San Gimignano's eventual decline. The town's population was decimated by the Black Death in 1348. Trade and pilgrims moved away, and the town lost its independence to Florence. It was only in this century that its fortunes picked up again with the arrival of large numbers of tourists.
The towers here were extraordinary for their day. The principles of their construction were simple but effective, based on experience rather than formal design methods. The fact that there are so many of them reinforces the atmosphere of commercialism and competition, everyone straining to outdo their neighbors.
At the end of the day, there's only so much you can do with stone. Traditional masonry buildings rapidly reach a limit in height when the external walls become unfeasibly thick because they have to support their own weight and the ever-increasing wind load. To build much higher than this, the walls at the bottom would have to be so vast there would be no space inside. It was only with the emergence of new materials in the 19th century that the development of the skyscraper as we know it truly begins. Although the details changed, basic building systems remained much the same for several hundred years, until the end of the 19th century. Then, the quest for height in Europe entered a new phase in places like this, Liverpool, a busy and prosperous international city.
This is the Royal Liver Building, widely regarded as Britain's first skyscraper. It was built for the Royal Liver Friendly Society. an insurance company who wanted a new headquarters which would reflect their role as insurers in one of the world's busiest ports.
Then, like now, this was one of the main points of entry to England from America, and the society must have aspired towards the new tall buildings that were all the rage in New York and Chicago.
The building is a 10-story office block with 2 6-story towers on the roof, giving a total height of 322 feet. Although its height is not unusual today, for 20 years after its opening in 1911, this was the highest building in Britain. The birds gracing the top are livers, a mythological bird said to have haunted the area.
The building is famous as a symbol of the city, but the attraction for me is its engineering. The Liver building was at the forefront of a new generation of European skyscrapers, which had a radical and innovative structural design. Unlike San Gimignano, the walls of this building don't have to carry the weight of the floors above. Instead, there's a frame inside which supports the whole structure. A frame is like a skeleton carrying the forces from bone to bone and eventually down to the ground. So the frame takes the weight and the walls are simply protection from the elements. The frame has another advantage. Using columns means that the space inside can be left empty, giving us the familiar open plan office. This was the great advantage of frame buildings. Big open spaces, which had previously been a luxury, were now accessible to everybody. The frame in the Liver building is made of reinforced concrete with steel bars embedded in it to give it extra strength. In Europe, at the end of the 19th century, the technique was pioneered by François Hennebique, a brilliant French entrepreneur whose designs quickly became standard practice. This was an Hennebique building.
The concept of the frame speeded up construction too. In fact, the building time for the frame averaged just 19 days per floor, an amazing achievement. Once the frame had been built up, work could start on the walls of lots of floors simultaneously.
The walls of the building are made of granite, 25,000 tons, mainly from Norway. The weight of granite helps to keep the building stiff. At the bottom, it's fine cut, but up here at the top, it's much rougher. Part of what makes skyscrapers possible is the services within it. A high-rise building couldn't be successful unless you can move the people up and down. So the invention of the lift by Elisha Otis in 1853 was critical to the evolution of tall buildings. And this is the lift motor room.
These are the original motors from 1910. They carry 6 lifts, and there are 4 more in the front of the building. This is actually fewer than in the original design because lifts are now much more efficient.
Other services are just as vital, such as controlling the temperature inside the building to keep it comfortable. This light well, one of 2 in the center of the building, provides light and ventilation throughout. This was in the days before air conditioning, of course.
Skyscrapers are also about showing off, as here in Liverpool, to the arriving passengers on the liners from America.
I'm directly behind one of the clock faces in the West Clock Tower. They each have 25-foot diameter faces. That's bigger than the clock face on Big Ben. But as for the bells, well, look, there aren't any. So how do the clocks chime? This is a bell tone generator dating from 1953. It's connected to a system of amplifiers and speakers, and it should be going off any second now.
The significance of the Royal Liver Building is that it marked the arrival of the concrete frame. It was a turning point in building construction, freeing up designers in an unprecedented way.
It might not look like a skyscraper now, but it was immensely tall to people then. Most importantly, it's a building which has all the elements that are important today. The concept of the frame, the lifts, a safe and comfortable working environment for the occupants. It was a blueprint for the future. But the Edwardian engineers could only have dreamt of where we're going next.
This building in Frankfurt, Germany, is the new headquarters of the Commerzbank. At 299 meters, it's the tallest office building in Europe. Its triangular shape was designed by the British architect Sir Norman Foster. The 56-story tower stands next to the bank's previous headquarters in the center of Frankfurt.
Despite its immense size, it fits quite comfortably with its surroundings. It seems to grow quite naturally out of the lower buildings around it. The modern building in front was designed to help it blend in and was in fact part of the scheme.
The main entrance is fully exposed to the street. Many floors have garden areas. It's a comfortable and popular working environment.
The main challenge with skyscraper design is to make them stiff enough to resist the wind, because wind forces increase rapidly with height. The stiffness of the Commerzbank comes from its rounded triangular shape. The Commerzbank is made up of 3 separate towers, one at each corner. Linked together by giant crisscross beams where the offices are. The effect is like 3 tubes bundled tightly together, which gives them much more stiffness when the structure tries to bend or is pushed over. The giant beams which join the towers at each corner are a special form of truss called a Vierendeel beam. Instead of the bars being diagonal, as in a conventional truss, they're horizontal and vertical. The main advantage of the Vierendeel beam is that the windows aren't obstructed, as they would be with diagonal bracing.
Conventional skyscrapers are built around a structural core in the middle of the building, but here the tubular towers at the 3 corners provide the main support. So in the middle, they can have a great atrium right to the top. That means the lifts are pushed out to the corners.
They've got some really fast lifts here. These ones go at 6 meters a second. There's a second challenge with modern buildings too. The Commerzbank had to satisfy the requirements of the local government in Frankfurt. They imposed a whole raft of environmental conditions to improve the energy efficiency and working environment of the building. This made the Commerzbank the first true eco-tower.
Buildings in Europe account for over 40% of all energy consumed. So in this building, the engineers paid particular attention to ways of reducing power consumption, but at the same time making the Commerzbank an attractive place to work.
The concept of the tower was to provide a light and spacious working environment. It's divided into groups of floors, like villages, each with access to its own separate outside garden space. Everybody has a view. The offices on the inside of the building look down on the garden, and those on the outside look out over the city. It's a great feature, both on a social level and for ventilation.
The central atrium controls the flow of air in through the garden and up and out at the next open level. There are ceilings every 12th floor for fire protection and to prevent strong updrafts from forming, which would spoil the tranquility of the open spaces.
This is the immediate difference you see compared to a normal air-conditioned office block. You can open the window. Here I am, looking down on my own garden space. Lovely.
And it's even more impressive when it's 20 floors up. But most importantly for the staff, with access to light and fresh air, no matter where you are in the building, it's a very attractive place to work.
On the other side of the building, the windows are also openable, but they have a second outer glass skin for weather protection. But it's still fresh air, and it comes up through the big gaps just here at the bottom of the window. There are conventional heating and cooling systems too, but for 60% of the year, the building is naturally ventilated, which is quite remarkable.
This is also one of a new generation of intelligent buildings. Computer-controlled systems can open and close the windows, reduce the lighting when it's not necessary, and move the lifts independently to more efficient positions.
People have talked about building skyscrapers a mile high. There's no doubt that with the knowledge and experience engineers and architects now have, there are no technical obstacles to that dream becoming a reality very soon. It's the design of buildings like this which will point the way. The construction of tall buildings is about self-importance, showing the world who's biggest and best. But in San Gimignano, Liverpool, and here in Germany, the quest for height has produced grand buildings of great beauty and vision. Skyscrapers are one of the most exciting challenges for civil engineers, and truly, the sky's the limit.
In the next program, we travel to Sweden to marvel at the most powerful wind turbine in the world, explore the largest pumped storage hydroelectric scheme in Europe at Norway in Wales, and get close to the ultra-high temperature technology of the Adela solar furnace in the south of France. In this program, we look at 3 buildings whose function is to harness the energy found in nature. We visit the giant solar furnace at Odelo in France and travel to Norway in Wales to see the mountainous hydroelectric pumped storage power scheme. But we start at one of the world's most successful wind farms.
Using the energy in the wind is nothing new, of course, and for centuries, small windmills like this have used the power of the wind to turn grinding stones or pump water for agricultural purposes. But modern societies consume enormous amounts of energy, and there are strong arguments for reducing our reliance on fossil fuels wherever possible.
Here in Sweden, on the island of Gotland in the Baltic Sea, energy is being extracted from the wind on a commercial scale.
This is Näsudden 2, the most successful wind turbine in the world, holding the record for the greatest amount of energy produced in 1 year, 7.7 gigawatt hours.
That's enough electricity to supply a community of around 1,500 homes with all the power they need. It's part of a large complex of turbines on Gotland, which are being used to develop even more efficient ways of generating power for the future. Wind turbines have to be in exposed positions, so they need to be simple to construct and maintain. They also need to be attractive so that they complement the natural landscape as far as possible. Näsudden 2's rotor blades are wider than the wingspan of a jumbo jet, and the concrete pylon is 77 meters high.
This gantry is used for inspecting the rotor blades, but it gives us a good chance to see the pylon. The pylon was built in 1982 for an earlier version of the wind turbine, a lower power model. It's built out of reinforced concrete, constructed by slip forming. That means the concrete was poured continuously while the shuttering was moved up, just like we are. The faint vertical marks you can see on the outside are left by the shuttering as the mould was pulled up the tower. Inside the wall, the concrete's heavily reinforced with steel bars that run up and down and all the way round, and that gives it the strength it needs to support the turbine on the top. The new turbine was installed in 1993. Like the old one, it was lifted up the pylon with its blades in position by winching it up these tracks here on the side. It weighed 200 tons and took 8 hours. They had to wait for perfect weather conditions to do it, which, as you can imagine in this part of the world, took some time. In fact, it was 3 weeks before there was a period with no wind, and they lifted it successfully to the top. They only just got there in time. After it was fixed down, the wind picked up just 1 hour later. We've locked the rotor so we can get out here and get a closer look at the huge 40-meter blades, one up above me and one down there below. They're made of a special lightweight carbon fibre composite inside a protective shell, so they have the strength and stiffness that they need. Even so, they still weigh 10 tons each, and when they're spinning, they're subjected to forces known as centripetal forces, trying to tear them off their mountings, up to 100 tons in each direction. So they're secured firmly to the rotor using this ring of bolts around the perimeter here. I'm in the machine house just behind the rotor. This is the gearbox here and the generator's just down below. It works just like the opposite of a giant electric motor. Instead of the motor driving the blades drive the motor, and that generates electricity. But the blades don't turn all the time. At low wind speeds, it isn't efficient to let them turn because all this equipment takes power to run it, 36 kilowatts in all. So when the wind is less than 5 meters a second, that's 18 kilometers an hour, the rotors shut down.
The wind blowing on the rotor and the pylon creates a drag on the exposed structure, trying to blow it right over. Its weight is 1,500 tons, and the foundation weighs another 1,900 tons. All this weight helps to stop it toppling over in the wind. But the shape of the structure is also critical to the design.
The shape of the pylon helps it to resist the forces acting on it from its weight and from the wind. If it was a simple cylinder, like I've made from this road map, it would be easier for it to topple over or to slide at the base, what's called shearing. But its flared shape gives it several advantages. It's much stiffer in bending and more difficult to topple, but also because there's more area at the base, it's easier for it to resist that shear force. The pylon is cast directly onto the concrete foundation here, and it's this joint that's critical to the stability of the whole structure. Steel bars which are embedded in the foundation rise up the walls, and they overlap with the steel bars which run up the sides of the pylon. That's how the structure resists the shear force from the wind, trying to tear the pylon and the turbine away from the base down here. It's a great sight, even in the mist. Naisuden 2 only runs at 2 speeds, 14 and 21 revolutions per minute, which are the optimum for the generator. It's running at 14 RPM now, and it may look slow, but the speed at the tip of the blade is 211 kilometers per hour, and the acceleration is 8.5 gravities. That's nearly 5 times your scary fairground ride.
It's a fine balance between the cost of the whole structure and the amount of electricity that it will generate. The higher you are, the higher the wind speed and the more power you can harness. But the building cost increases very quickly. This is the optimum design for the most powerful wind turbine in the world.
Naisuden 2 is a prototype, pushing the limits of what's possible with wind power. We've seen that the wind turbine is a simple structure, easy to build and operate. While wind farms like this currently only produce a small proportion of the national need for energy, it's clear that in future they could make a much greater contribution.
Electricity is a modern convenience we all take for granted. Whenever we flick a switch, we never doubt that our needs will be met in an instant. The problem is that at certain times, like at the end of a TV program or during the adverts, millions of kettles and lights are switched on all at once. It's a daily problem that requires an instant response. The simplest solution is to harness another of nature's elements, the immediate power of falling water. The challenge would be to design a system that could work on an unprecedented scale. This is Norway in Snowdonia, North Wales. Hidden under this mountain, below the level of this lake, is an instant response power station powerful enough to keep the whole of England and Wales from blackouts every day. Its construction required over 5 million tons of rock to be excavated and was the largest civil engineering contract in Britain's history, taking 6 years to build. It's the biggest hydroelectric pumped storage facility in Europe. Yet in spite of its size, it's so well hidden that visitors barely notice it at all. The locals call it Electric Mountain.
This is how it works. This is the mountain, and there's a reservoir at the top called Machlan Mar. There's a tunnel that runs from the reservoir into the heart of the mountain and then down to the power station at the bottom, and another tunnel that runs out to this lake here. There's a gate at the top to control the flow and a surge tank to control the pressure. During the day, the water runs down the tunnel and falls down to the power station at the bottom, where it turns the turbines, and it's then expelled to the lake at the bottom. At night, when electricity is cheaper, the water is pumped back up through the tunnels and into the top reservoir, which is filled up again.
This overnight pumping is essential because the huge volume of water needed every day is too great to be replenished by rainfall or rivers.
This is the reservoir at the top, and it holds 7 million tons of water. That's 6 hours' supply.
The original lake up here was too small, so this dam was built to give the system greater capacity. Its elegant design blends smoothly into the landscape.
I'm deep inside the mountain, just below the reservoir at the top, and these two huge gates on either side mark the entrance to the tunnel taking the water down the mountain to the power station. You can get an idea of the size of the tunnel from the size of the gates. They're absolutely enormous. This is the surge tank above the water intake tunnels. The reason for the surge tank is to absorb the water shock waves, a bit like the juddering in your pipes at home when you open or close a tap too quickly. It's a straight drop of 500 meters from there to the bottom. That's deeper than much of the North Sea.
As the water approaches the power station, the main tunnel splits into 6 smaller tunnels, each heading for its own turbine generator. The tunnels narrow to increase the speed of the water. There are more than 16 kilometers of these tunnels, all beautifully lined in concrete to allow the smooth transport of the water. This is essential, as any rough motion of such a large quantity of water could damage the tunnels. I'm now driving into the heart of Electric Mountain, down towards the station complex, where the falling water finally generates the electrical power. This access tunnel is about the same size as the main water tunnel.
Just imagine that running full of water at 18 kilometers an hour.
These are the 6 inlet valves connecting the 6 water tunnels to the 6 turbines. The instant these valves are opened, water rushes through, and in 10 seconds it's driving the turbines. It's like having 1,800 megawatts of power on tap.
That's the fastest response time of any power station anywhere in the world. This is the machine hall above the generators, and it's absolutely enormous. We're in a rock cavern, 2 million cubic meters in size. That's big enough to house St. Paul's Cathedral in London. The bare rock is reinforced with rock bolts, like this big one behind me, which are like nails drilled into the rock and then tightened up to hold it all firmly in place. The water finally comes out here in Llyn Peris, the reservoir at the bottom of the mountain. From here, tonight, it will be pumped back up through the turbines and the tunnels to the reservoir at the top. And tomorrow, it will all be back down here again, all 7 million tons of it.
To be able to generate enough power to run a city at a moment's notice every day is a daunting challenge. It was a bold decision to build a massive complex inside a mountain. But De Norweg has proved an outstanding success, technically and environmentally. You'd hardly know it was there at all.
The instant power which De Norweg generates serves a nation, meeting a demand from millions for instant electricity. But the fundamental source of nature's power isn't wind or water, but the sun. What if we were able to tap the sun's radiation directly?
This is the huge solar furnace at Odélo in southwest France. Its purpose is not to generate electricity at all, but to trap sunlight and focus it onto a single spot, generating incredible heat over a very small area. It's the biggest solar furnace in the world.
The energy from the sun reaches the Earth here with a power of about 800 watts per square metre, say 8 light bulbs. Enough to burn you on the beach, but not enough for the scientists to work with. The challenge was to build a furnace that could focus over 1 megawatt of power onto a target little more than the size of a soup plate. Such a furnace would need to collect all the heat from the sun over a large area, over 2,000 square metres. That's 8 tennis courts.
By using an array of mirrors, this large area of sunlight can be concentrated onto a relatively tiny focal point.
The principle of the Odélo furnace is really very simple. This is the hillside. At the bottom of the hill is a huge parabolic reflector facing the hillside. It's 50 meters high. To channel the sun's rays, mirrors on the ground track the sun's movement across the sky and feed the rays into the parabola, which in turn reflects them to its focus, where the furnace is located. Each mirror is targeted at a different section of the parabola, but all the energy ends up at the furnace, like this, where the temperature can reach 3,800 degrees centigrade. That's enough to melt steel armor plating. This is Le Champ des Héliostats, the field of heliostats. A heliostat is a wall of mirrors which can be moved using motors to follow the sun, reflecting the sun's rays directly into the parabola. There are 63 heliostats on terraces up the hill, each one with 180 panes of glass. The glass on these mirrors is as flat as possible to reflect the sun's rays without distortion towards the parabola. Each heliostat is aimed at a different part of the parabola, and together they cover the whole surface. The area of all the heliostats is slightly greater than the area of the parabola to allow for some overlapping of the images.
Each one is controlled by a computer and can be aligned within seconds with the precision of 1/60th of a degree. That means that a sunbeam hits the same spot on the giant parabola with an accuracy up to 3 centimeters. The scale of the building can really be appreciated as you begin to climb the 9 floors behind the parabola. Even here, it's still 18 meters out to the focal point.
There are 9,000 individual mirrors on the parabolic wall. Each one is slightly curved to improve the concentration of energy at the solar furnace. The more perfect the parabola, the more focused and therefore the more intense will be the sun's rays at the target. Behind this facade, we can see how they're all mounted. Of course, the mirrors on this wall don't need to move, but they do need to be firmly secured against the wind and the elements, and that's what these grey mounts are for. The glass on these mirrors was specially heat-treated so that it could be bent without snapping. This bolt in the middle pulls the mirror back so that it's curved. Each mirror was tuned by hand to its perfect position. It took nearly 3 years to complete. The mounts holding the individual panes are in turn supported by this steel space frame, which is fixed to the 9-story building behind. The building was constructed from reinforced concrete to minimize thermal contractions and expansions between winter and summer.
Such contractions could distort the shape of the parabola. We're 1,500 meters up in the mountains here, and seasonal changes are much more extreme than at sea level.
This is the sharp end of the laboratory, the furnace, where the sun's rays converge on this hole here. It's like being at the tip of a welding torch. Behind the hole, there's an experiment in this capsule waiting to be tested. It's a disk of new material, like this, which will be used in the heat shield of a space probe going to the sun in a few years' time. Conditions in this capsule are positively out of this world. They simulate the exotic environment close to the sun. Extreme temperatures, 2,500 degrees centigrade. I love research laboratories, it's great.
Odelo Solar Furnace is a world-class research laboratory where engineering and science come together in pursuit of new, high-performance materials. It's also an extraordinary structure, a building in which function entirely dictates form.
Harnessing nature's power on such a scale is one of the greatest challenges for an engineer. To capture the power of the wind in Sweden, the mighty force of water in Wales, or the heat of the sun here in France, required vision and ingenuity. In this extraordinary field of engineering, where special applications require special structures, we are only limited by our imagination. For thousands of years, mankind has been drawn to caves and caverns in search of shelter and raw materials. But it's only recently that we've exploited underground space on a large scale, and not just for minerals.
In this program, we travel to Norway to see the largest rock cavern in the world in public use, and visit the deepest excavation ever undertaken in London as it nears completion. But we start at the deepest mine in Western Europe, on the northeast coast of England. This is Bulby, on the edge of England's Yorkshire moors. It's home to Britain's only potash mine, supplying the mineral potassium chloride, essential to agricultural fertilizers. It's a relatively modern mine and uses pioneering techniques for creating underground space. For centuries, mining has presented us with the same problems and dangers. It's not easy and it's not pleasant, but if you want the treasures of the earth, then you have no choice but to go deep underground.
Right, let's go. It's a hostile environment. Mining is difficult and potentially dangerous work. But if you're successful, it's a lucrative business. The challenge is how to dig away at the very matter that's holding the roof up above your head. Thank you. To get to the potash seam, we have to travel over 1 kilometre down into the Earth's crust and then drive 8 kilometres out under the North Sea. Great. Thanks. All right, let's go.
We're now in a pre-Triassic world. The seam that they are mining was formed as part of the bed of a prehistoric sea which reached as far as what is now Poland.
This sign marks the end of the coast. From here on, we're under the sea.
It takes half an hour to reach the face. It may look dank and dingy down here, but it's actually incredibly hot, 40 degrees centigrade. The reason is we are closer to the molten rock beneath the Earth's crust. Not much closer, but enough to make the difference.
Yesterday, this was solid rock, which had been sleeping here for hundreds of millions of years. And by the end of the day, they'll be 7 meters further on. In a few weeks' time, it'll all be gone. It may seem that they're just boring away, but in fact the tunnels are part of an ingenious structural design which combines geology and engineering expertise to create a controlled and safe space.
This space is supported without any additional propping. Instead, they create the supporting structure by carving out the existing rock into pillars and arches, just like a church. The weight from above is channeled to the carved rock pillars on either side. The really clever part comes in creating a single super arch to span over the individual arches of several tunnels.
It works like this. This is the seabed, way above us. If you drive a single tunnel by itself, then a small arch forms naturally over the top. But the weight of the rock above, all the way to the surface, is still bearing down on it and squeezing in from the sides. Driving several tunnels together can solve this problem. What happens is that as the roof starts to sag, a giant arch forms naturally right over all the group of tunnels together, throwing the weight from the rock above out to the sides. It's still squeezing in, but not in the middle. That leaves this section here, which is now detached from the rock above. It's bearing down on the tunnels in the middle, but now the force is much less. The walls between the tunnels are allowed to crush slightly as the roof bears down. Here you can see the cracking of the rock vertically. Eventually that will break away, leaving an apple core shape like this, tapered in the middle. Of course, all this rock is like money to the mine. The incentive is to excavate everything that can safely be removed.
Striking the right balance between how much to excavate and how much to leave as support depends on constant and thorough geological study. Just looking at the appearance of the exposed rock can reveal a lot about how it was formed and, critically, how it will behave.
All these rocks are sedimentary. That means they were laid down as loose grains and eventually squeezed together to make rock. 240 million years ago, all this rock was being formed on the seabed. These layers show the sedimentary process, winter and summer, as grains fell to the bottom of the sea, exactly like the rings on a tree.
The geologists also send probes down boreholes drilled at precise inclines into the rock face. These provide essential information about the direction of the potash seam and how wide they can safely excavate the tunnel. A graph is drawn of what lies ahead, and precise instructions are painted onto the rock face itself for the miners to follow.
Here we can see the roof of the tunnel sagging and starting to collapse under the weight of the rock above. It looks risky, but the whole life of the tunnels and the space can be mapped out, provided the geology is thoroughly understood. And here you can see the final result, the collapsed roof. It's been allowed to collapse to protect the working tunnels next door. It may stay like this forever, or it may eventually converge, squeezing together. The Boulby mine is a leading example of the latest in mine design. Here they're creating space for a very specific purpose and for a short duration. But it isn't a place for the public. If you want underground space which the public can use, it has to look rather different.
This is Yorkshire, a small town 140 kilometers north of Oslo, an historic trading centre on the shores of Norway's largest lake. In 1988, it was announced that the Winter Olympics would be held in Norway in 6 years' time. Yorkshire was chosen to host part of the ice hockey competition. Top of the to-do list was build a stadium. In a small town like this, a conventional stadium here on the surface would have stuck out like a sore thumb. Building it underground would solve that problem.
The challenge was how to create an underground space vast enough for an Olympic stadium. You enter the Yorkshire Stadium through a 120-metre-long tunnel which runs deep into the mountain. The lighting is specially designed to give you a feeling of entering a subterranean world. Compared to the rough and dirty environment of the mine, this is almost clinical in its cleanliness.
The Mountain Hall at Yorkshire is one of Europe's most extraordinary civil engineering achievements. This ice rink is the largest rock cavern for public use anywhere in the world. Walking from that tunnel into this huge space is quite magical. This is a stadium with seats for 5,800 people, but we're 50 meters below the surface of the mountain. The whole space is wide enough for a football pitch and tall enough for an 8-story building.
Normally, you associate underground space with being small and close, but this is quite the opposite, light and spacious.
This is because the huge roof needs no columns or props to hold it up, so the space underneath is absolutely clear. So how did they create this permanent space and stop its vast roof from falling in?
It may be big, but it's been built using tried and tested techniques. This is the mountain and the cavern with its rounded roof. The natural fractures in the rock above break it up into blocks, which could fall down. To prevent this happening, the roof is strengthened using rock bolts. These are steel bars pushed into holes drilled deep into the roof and cemented in position. By locking the whole roof together, they create a sort of dome over the cavern, and this is the ideal shape to carry the weight of the mountain safely to either side. Tusen tack. I can show you how the rock bolts work with this lump of Norwegian cheese. It's very simple. Like loose bricks, the blocks of rock in the roof would fall down over time if they weren't held firmly in position. The bars link all the blocks together so they can't move independently. So effectively, the rock mass acts as one and is locked together in 3 dimensions by the bolts. It's a lovely igneous rock called gneiss, funnily enough. Beautiful red colour. And that's a hole for a rock bolt, right there. And here's another one where you can actually see the steel tendon sticking out of the rock and the cement around it where it's been set in place. This one's been cut off so that people don't tear their clothes when they walk past. Up here, I'm between the metal skin of the roof and the rock itself. This is one of the rock bolts just sticking out over there. The metal roof is hanging from the rock on these blue bars that you can see in the distance. They excavated the cavern by drilling and blasting. 29,000 truckloads of rock were taken away. It's amazing. One of the great advantages of building underground is that the ground insulates the space. Down here, the rock is an absolutely stable 8 degrees centigrade. That's a lot warmer than outside.
The temperature of the seating areas and corridors is easily raised above this rock temperature to a very comfortable 16 degrees centigrade. This is achieved by recycling the waste heat produced by the ice refrigeration machines.
It's much colder on the ice, and that's largely because the silver reflectors up above bounce the cold back down again and keep this whole area freezing. In fact, being underground is very economical. Energy consumption is just 50% of a conventional stadium, and maintenance costs are minimal because it's entirely protected from the elements. The stadium has another side to it altogether. It's designed as an air raid shelter for the town, capable of taking 2,000 people. The whole complex can be sealed off using these huge doors, and life support systems can protect the occupants for up to 48 hours.
The Yorkshire cavern is an outstanding example of how engineering underground can create an excellent leisure space for the general public.
But in reality, few of the major cities in the world are built on rock. When it comes to digging down in soil, an altogether different approach is needed, as we shall see next.
London is one of the greatest cities in the world. It's exciting, busy and congested, with fewer and fewer sites left for essential new buildings.
One solution is to build upwards, but another, as we saw in Norway, is to build downwards, exploiting that space underground. This is the new underground station at Westminster, in the final stages of completion. Under this ticket hall is the deepest excavation ever undertaken in London, the same height as a 12-storey building entirely underground.
The station is being rebuilt to accommodate the extension of London's most modern underground railway line, the Jubilee Line. With sites such as Big Ben and the Houses of Parliament next door, it's destined for heavy use. In fact, 10,000 passengers will pass through these gates every hour. Tunnelling the rail link is comparatively straightforward. The daunting part would come in digging a hole big enough for 4 lifts, 6 staircases and 17 escalators. Holding back the earth from such a vast space is especially difficult here, where the soil is almost pure clay. This clay is not only soft, but also sponge-like, prone to swelling as it draws up water from all around.
The challenge for the engineers was to build this huge new station complex deep into the clay soil underground without disrupting the existing station and, critically, without threatening the foundations of its famous neighbour across the street.
The obvious shape for the structure was a giant box protected by deep walls on all sides. Simply digging a big hole for the box would be very risky because the sides would cave in. The trick is to put the walls in first.
Here I can show you how it's all laid out. This is ground level. The deep slots were made in the ground around the box, like this. Steel mesh was dropped in, and the slots were filled up with concrete to make the walls. Of course, there's still soil inside, and if they'd started digging now, the walls would have caved inwards. So they had to build the floors first to keep the walls apart. This meant they had to start at the top with the top floor, and then they dug out the soil underneath and fitted a strut. And then they dug out the soil underneath that, fitted another strut, and so on, right the way down to the bottom. In fact, it's so deep, you could almost fit the Tower of Big Ben inside. This is the deepest underground space in London, and yet it feels more spacious than many ordinary buildings. It's only possible because of the ingenious system of struts and walls that allow this great box to be built deep underground. The wall around the box, which was built first, is called a diaphragm wall. It's made of reinforced concrete, and it goes all the way from the ground surface down to below the bottom basement. It has to withstand the pressure from the soil and the water in the ground outside, which is constantly trying to push it inwards, so it's over 1 metre thick. It looks rough, but of course the concrete is just poured into a slot cut in the ground, using the clay itself as the mould, and then that soil is just dug away, leaving this surface. It's very impressive, really. The diaphragm wall is further stiffened by these concrete buttresses, which run up and down, and beams which run from side to side. And they carry the force from the ground outside into these huge steel struts, which span from one side of the box right across to the other. They each weigh 60 tons, and it's 24 meters across the width of the box. Using struts like these allows the space inside to be as clear as possible, which is what the designers wanted, a feeling of openness. Even here, deep underground, you can see right up and down the building.
This great underground structure in fact does more than hold back the wet London clay. It also provides a solid foundation for new construction on the surface. 6 floors of a new parliamentary building are being stacked above the station. The ingenious underground box design is a template for metropolitan development. It proves that anywhere in the world, even with limited space on the surface and soft soil underneath, buildings may be constructed both above and below ground level without creeping into the skyline or sprawling into the countryside.
Our understanding of how to work with soil and rock has developed massively over the years. From tunneling mines and excavating rock caverns like the one we saw in Norway, to the sophisticated solutions for building deep under metropolitan London, our technology has advanced to meet society's every demand. There is huge potential for using underground space even more in future. What's exciting for me as an engineer is to meet that challenge, to create that space.